Hey! Today I'm gonna present you a mathematical concept called the PID controller. Sounds unfamiliar? Well, probably you haven't heard about it, but I can assure you that you have met it a dozen of times. We've got 3 minutes, so let's go! PID controllers are implemented in countless devices you might have even not heard about. This includes humidity, temperature, pH neutralization or speed controls, and almost any other systems which involve regulating a value which has an impact on the future input. PID controllers are structures and their algorithm implementations that adjust the so-called process variable PV to a given setpoint SP and are widely used in industrial and commercial applications, thanks to their flexibility and sufficiency. What makes PID controllers special amongst other algorithms is their feedback mechanism. What does this actually mean? Well, a feedback occurs when a system's outputs are routed back as the system's inputs. This enables PID controllers to react to future signals with regards to their previous outputs and their effectiveness. In simple words, it helps the system to tell how strong or weak should it react to an input based on how the previous outputs influence the error. Moreover, PID controllers are easily accessible for everyone. I even implemented them on my own in my DIY drone based on a Raspberry Pi. As you might have noticed, most of the video was filmed from an aerial camera created by a drone which, apparently, wouldn't fly at all without PID controllers. In a perfect world, the drone would simply power the motors and they would equally lift it up, but in the real world the mass of the drone may be badly balanced, or the wind might tip the drone in any direction, which couldn't that badly. PID controllers adjust the speed of individual motors to compensate the tilt and maintain attitude. A PID controller consists of 3 terms: proportional, integral and derivative, which are tuned by 3 non-negative gain parameters. The values of all terms are then summed and produce an output value. There are more variations of PID controllers created by a selective use of control terms. For example, the popular PI controller, which has the KD gain set to 0, is less sensitive to measurement noise. The proportional, which is basically the multiplier of the error, considers only the current value of error. It increases the speed at which the current value approaches the setpoint, but also creates an overshoot. Next, the integral. As you know from maths, integration is continual summing. This means integration of error is summing up the controller error history over time. The integral considers how long and how far has the PV been from the SP over time, accumulating the effect. The last term is the derivative. As you might remember from the differential calculus lessons, we can use the derivative of a function to find points in which it changes its direction. The derivative term greatly decreases the overshoot and settling time, while not considering how far the PV is from the SP, but only how the PV changes, how quickly its value rises or decreases. Provided you had ever needed a control algorithm, from now on you will have an amazingly simple but mighty solution, definitely worth 3 minutes of video.